For our linear systems module, we're going to do two topics: solving systems with two unknowns and solving systems with three unknowns. So this video is going to cover the two unknown situation. So when you have two unknowns, you're going to have two equations. When you look at this slide, there's a lot going on in terms of A1s and A2s and all this stuff. So what would this look like in real life? This could have been something like 5x minus 3y equals 22. Or, 2x plus 7y equals 0. So A1, B1, C1. They're just numbers. They're coefficients with the variables and a constant on the right side. So what happens is there may be a point, xy, which will fit into both of these equations and make both of them true. We can think of this graphically. If the situation I described in the previous slide happens where there is a point that fits, that point can be represented as the place where two lines cross. It works algebraically and it'll work graphically. And that means you have only one solution, because if you have two straight lines, they can only cross in one location if they're going to cross like this. And we call that an independent or a consistent system. Most of our examples will be like this. You'll do the math and you'll end up solving for a point of intersection. Sometimes I call that the POI when I'm writing it down. The other thing you can have when you graph is parallel lines. And when you have parallel lines, they can never cross. They'll go on infinitely in either direction, never crossing. So there will be no solution for the system. And when we'll see what the math looks like when that happens later on, and we call these inconsistent or no solution systems. The third situation that could come up is that we have a line, and then we have a second line that appears exactly on top of it. So like an equivalent line. And we say this has infinite solution because these two lines are in contact with each other at all points. So we say they're coincident, and we call it a dependent system. Here's a graph, revisiting the graphs, and we see we have two equations. I'm going to call the top one A, and I'm going to give it I guess it'll be my blue line. I thought it'd be my red one, but it looks like I'm committing to blue. So first thing I'm going to do is I'm going to graph this line and see where it lies. So I know that I want to change that into slope-intercept form. That's my go-to. So I rearrange it into y equals negative 3x plus 5, where I have a slope of negative 3 and a y-intercept of 5. So let's plot this line. I go to my graph. I'm going to go to the y-intercept, which is 1, 2, 3, 4, 5, and I put a dot there. And then I look at the slope. If it's negative 3, that means the run is down 3. So back to here. And then if I don't see a denominator, I know that I think I said the run is down 3, but I meant the rise is down 3. If I don't see a denominator, that means the run is right to the 1, as it always is. So now I'm going to go pick up my line here and try and set it up. So it crosses everything. I'm going to drop it on one point, spin it. Come on, baby. So no, spin it. I'll give it one more time, and then there's some re-recording going on. There we go. So it crosses through the second point. Then I'm going to extend it and kind of clean it up a bit so I get those 2 points. Painful. Okay, good enough. To go over to our second line. Suffer the same thing again. Line B. All right, going to rearrange again. A few more steps here. 3y equals negative x minus 9. I need to divide the equation by 3 to isolate y. And I get y equals negative 1 over 3x minus 3. Okay, so what happens with this line? It's going to have a y-intercept of negative 3, which is right here. The rise is negative 1, so that means I go down 1. And the run is 3, and I go over 3. 1, 2, 3. So between those 2 points is where I want to hit. Let's go put this guy here, right at the edge, so when I spin he doesn't go away. And then we'll spin this guy over here, extend him, and extend. And here's the beauty of graphing. What was my point supposed to be? I would say that I probably got my 1 wrong, and the point I was aiming for is probably a nice integer point right here, which is 1, 2, 3, 3, comma, -4. How do I know if I was right when I'm graphing? Check your answer in one of the equations. In equation A, 3 times 3 minus 4 equals 5. 9 minus 4, that's 5. 5 equals 5, that's correct. Now, really double check with the second equation. In equation B, 3 plus 3 times -4 equals -9. Is 3 minus 12 equal to -9? -9. Yeah. All right, we're golden. Here's another graphing example, and we're going to go through and do the same thing we did. Take line A, x minus y equals 1, and we're going to have, I'm going to move the -1 over to this side so that I get y positive, and if you don't like the look of that, y equals x minus 1. This tells me that for line A, I'm going to have a y-intercept of -1. And if I see nothing in front of the x, that means the slope is 1. And I just go up 1, right 1. I've spared you the pain of watching me try and put the line on the graph and put it on myself. Well, the recording was paused. So let's look at line B here. Okay. I want to rearrange this, so I'm going to start by flipping the 2y over here on the left side, and then I'll move x and the y-intercept over, and that will turn into 2y equals x minus 4. Isolate y by dividing everything by 2, and I will have y equals 1/2 x minus 2. This tells me my line is going to start at -2. And it's going to have a rise of 1 and a run of 2. So my next point would be here. My red line has been added to the graph, and I can see the point of intersection appears to be right here, and the coordinates for that point would be -2, -3. How do I know if I'm right? You can check them in the equation. So in equation A, I replace x with -2, and I replace y with -3. And I check to see whether the equation is true. Is -2 plus 3 equal to 1? Yep. So you know you're right for that line, and you would do the same thing. Check it in B to make sure you're correct. One last example for graphing. Going with line A, rearranging it into y equals mx plus b form. 2y equals -3x plus 8. Y equals -3 over 2 x plus 4. Our points for that, starting at the y-intercept, which is 4, and then our rise is -3, so we go back down 3 to here, and our run is 2, that's always to the right. Here's our next point. Line A has been added to the graph. Looking at line B, let's rearrange. -4y is equal to 6x plus 12. We're going to divide out the -4, and we're going to get -6 over 4, which is -3 over 2x minus 3. And we'll plot that on our graph, starting at -3. And this might look familiar. Your rise is -3, so you go down 3 over 2. And our next point will be here. Blue line added, and look at that. We have 2 parallel lines. So this particular system will have no solutions because there's no point of intersection. Parallel lines will never cross. How could we have known? Look at the slopes. Both of them have a slope of -3/2. They are parallel. We didn't even need to graph it. Everyone hates to solve systems by graphing, and it isn't perfect, because if you don't have a beautiful point like 2, 1, then it gets really hard to see where the point of intersection might be, and you're guesstimating, right? And then you're subbing in and doing math anyway, so why not just do math from the start? We're going to look at two ways to solve the systems, substitution and elimination, and we'll start with substitution. So the procedure here is just a list of points. We're going to isolate either x or y. I don't care which one you do. And we're going to look for the easy equation to do that. So usually we're looking for an equation that already has x or y with a coefficient of 1, so a plain old x or a plain old y. And we'll rearrange that equation to make x equals or y equals. Then we're going to take that solution and we're going to sub it into our second equation and solve for the variable that we didn't isolate, the second variable. We're going to do some math and we're going to get, x equals or y equals. We take that number, because it'll be a number now, and we're going to put it back into the equation we rearranged and solve for the first variable. And then we're going to check our solution. So that's a lot of talking that makes no sense. Best seen by example. All right, we've got two equations. I'm going to call them A and B. Now, I notice that A has an x sitting all by itself. So that's a variable I'm going to isolate. I'm going to isolate x in equation A because it's easy. I don't have to do dividing. I don't have to do extra stuff. So if I rearrange equation A, I get x equals 5y minus 34. Okay? So this is a value of x. I've got an x in the second equation that I can replace with this sentence, because that's what x equals. And if I'm going to have these two lines crossing, x and y are the same at that point, so it should work for both. So here we go. Looking at equation B becomes 2. Replace the x with 5y minus 34. Write down the rest of the equation as you see it. And here on in, it's just algebra. We're going to distribute 10y minus 68 minus 5y equals -28. 5y, and I'm going to send the 68 over to the other side where it'll be positive, equals -28 plus 68, which is 40, and y equals 8. All right, I found a value for y. I'm going to go back up here and solve for x. X equals 5 times 8 minus 34. 40 minus 34 is 6. I am proposing that the point of intersection of these lines, where they cross, is 6, 8. That is a solution. I better check my answer though. I just used equation A to find x, so I'm going to use equation B to check my answer. Is 2 times 6, the x value I found, minus 5 times 8 equal to -28. If it is, I've done everything right. If it's not, you made a mistake. Go back and start over. 12 minus 40 equal to -28. Left side equals right side. You solved it correctly. One more example of substitution. So here's my equation, A and B. I'm going to call equation B the easy one because I see this loose y with no coefficient. So I'm going to rearrange equation B to isolate y. Y equals 5x minus 3. Okay. I'm going to replace y in the first equation with that algebraic expression. So here we go. Equation A is going to now look like 3x minus 8, and here's a y substitution. Great. Now I only have one variable, so I can solve for x. 3x minus 40x minus 24. Oh, sorry, plus 24 equals 24. That was about to be a very different equation. And we're going to have negative 37x equals 0. Do not despair. X is going to be 0 divided by negative 37, and x will be 0. Totally fine. I'm going to take that value and I'm going to bring it up to my rearranged equation and solve for y. I've got x, now I need y. Y equals 5 times 0 minus 3. So y equals negative 3. So I propose these two lines cross at the point 0, negative 3. They cross at the y-intercept. Okay, let's double check. We used a rearranged version of b to get our y value, so let's check our answer in the one we didn't use, equation A. So is 3 times 0, that's equation A, minus 8 times negative 3, negative 3, equal to 24. 0 plus 24 equal to 24. Absolutely, left side equals right side. You solved it correctly. Okay, we've done graphing and we've done substitution. So our last way to solve a system of linear equations that we're going to look at is elimination. Once again, here's the talking slide. So what you're going to do is kind of set the equations one on top of the other, or in the form, 3x plus 2y equals 7. You're going to look and you need to make either A or B the same or opposite. So if you have 3x and something in the first equation and negative 3x and something in the second equation, you are set up for elimination. Then you're going to add and subtract the equations. That will get rid of one of your variables. You'll solve for that second variable that's left behind. You'll take your answer, sub it back into one of the original equations, either A or equation B, and you'll find the other variable and you'll check your solution in both equations. Talkity talk talk. Let's look at the actual stuff. Okay, so here I would use substitution because that's my preferred method, but we're not going to because we're learning about elimination right now. I've got equation A and equation B. And as I look at these equations are set up perfectly to eliminate y. And how will that happen? I stack the equations one on top of each other, or just rewrite them. And then I'm going to just kind of do old school math. I'm going to add the equations together. X plus 2x equals 3x. Now, negative 3y plus 3y equals 0. So I've eliminated the y from this equation. And 6 plus 3 equals 9. So I can solve for x. X equals 3. Now, I'm going to take that value I just found and put it into either equation or B. It doesn't matter. Both of them should work. So I'm going to use equation A. Replace x with 3 minus 3y equals 6. I'm going to move the 3 up to the other side, leaving me with negative 3y equals 3, and I divide both sides by negative 3 to get y equals negative 1. So I'm proposing that the point of intersection, the solution for these two lines where they cross, is 3, negative 1. I used equation A to figure this out, so I'm going to use equation B to double check my answer. Is 2 times 3 plus 3 times negative 1 equal to 3? Is 6 minus 3 equal to 3? Yep, you're right. System solved. Another example, not as pretty as the other one perhaps, but a perfect one for elimination. So I've got these two equations, A and B, and there's no matching coefficient. The number in front of the x's is not the same, the number in front of the two y's is not the same, but they could be if I manipulated one or both of the equations. Now, for me personally, I love to have equations with opposite signs. So if I take equation A and I multiply, or I double the entire equation, multiply it by 2, it becomes negative 10x plus 4y equals negative 8. And then I have the x's set up perfectly for elimination. So here I go, rewriting them, one on top of the other. adding the equations together. Negative 10 plus 10x, those are going to vanish. 4 plus 3 in the y's will make 7. And negative 8 minus 6 is negative 14. Should have left the y behind. All right. And we're going to isolate y, and we're going to end up with y is equal to negative 2. I'm going to go back to equation A and solve for x. Negative 5 times x plus 2 times negative 2 equals negative 4. Negative 5x minus 4 equals minus 4, and we have a situation where negative 5x equals 0, and we know from our previous example that just means x equals 0. So I think my answer, the point of intersection, the solution to this equation, set of equations, will be 0, negative 2. But I better check. I will check it in equation B because I just use equation A to find x. So is 10 times 0 plus 3 times negative 2 equal to negative 6? Is 0 minus 6 equal to negative 6? Yep. Equation solved. Or system solved. I keep saying equation. Here's another one. Nothing pretty. Maybe I'll do the x's. I could change the 5x into 15x. I could change the 3x into 15x. All right, so for my top equation, I'm going to multiply it by 3 to make an equivalent equation that has 15x in it. So I'm going to end up with 15x plus 24y equals negative 15. My bottom equation. So this is my own personal thing that I like to do. I always like to set up, so I'm going to change it so this equation B has a negative 15. So instead of multiplying by just 5, I like to multiply by negative 5. I find this easier than trying to subtract equations. People always mess up when they do elimination with subtraction. I always keep elimination with addition by setting up opposite coefficients. All right, so if we're going to multiply this by negative 5, we create negative 15x plus 25y equals 15. I'm going to do it right here. You can see where this is going. The x's are going to cancel. I have a truly horrific coefficient in front of the y's, but that's fine because my my constants are going to add up to 0. So y is equal to 0. It's been very kind equation so far. I am going to solve for x in equation A. 5 times x equals negative 5, because 8 times 0 is 0. X equals negative 1. I think the solution to the system is negative 1, 0. But I'm going to check in equation B. Is 3 times negative 1 minus 5 times 0 equal to negative 3? Negative 3 equals negative 3. That is true. You found the solution. And the last slide I want to look at today is going to talk about those inconsistent and those dependent systems. So inconsistent, parallel, no solution. Dependent, equivalent lines. Okay, and I'm just going to see how the math plays out when you try and solve this. First of all, this is a hot mess. Let's rearrange this this number 1 here so it looks at least familiar. Negative 6x minus 5y equals negative 12. Negative 12x minus 10y equals negative 14. Okay, so be it. So I want to set up for, I think I will choose to do elimination. And what I'm going to do is multiply the top equation by negative 2. Okay, so I'm going to rewrite again down here. And I multiply by negative 2 to make a positive 12. And I'm going to end up with 12x plus 10y equals 24. And that's equation A rewritten. And I'm just going to rewrite B as is, minus 10y equals negative 14. I'm going to continue with elimination, and I'm going to have 12 minus 12 is 0. Whoa, plus 0 equals 10. 0 equals 10. I ran out of variables. I didn't solve this. I just accidentally disappeared my x's and my y's. So if you get to a point mathematically where you find something that is never true, 0 is never equal to 10, let's think of it as logic, those lines never cross. That is parallel. So mathematically, this is what parallel lines look like. The numbers might be different, but it's going to be something that makes no sense. And now we're going to look at number 2. This one I'm going to use substitution because I see this beautiful x all by itself. Rearrange this equation. X equals 3y plus 9. And I'm going to substitute it into my equation b. Negative 2 times 3y plus 9 plus 6y equals negative 18. Okay, negative 6y minus 18 plus 6y equals negative 18. And I'm kind of getting to the same place. I'm going to accidentally eliminate my second variable, and I'm going to end up at a statement that is always true. So negative 18 equals negative 18. That's always true. So if you see your equations fall apart and the math ends up at something that makes sense and is always true, then you're dealing with a dependent or an equivalent line system where you have infinite solutions. All right, so know when you do your math, that might happen.